Hello, everybody, and thank you for coming for Indie's Journal Club series. This is a great series on Twitter doing journal clubs of papers that are being talked a lot about. And today we have for you class switch toward non-inflammatory spike-specific IgG4 antibodies after repeated SARS-CoV-2 mRNA vaccination. This paper was published in Science Immunology, a very high-impact journal, and it's been getting a lot of talk lately in the Twitter spaces and elsewhere on the internet. A lot of misinformation going around about this paper, but to start, I'm just going to go through it as if misinformation doesn't exist, and we're just reading this paper as a scientific audience. So let's jump right into the introduction. So the introduction of any paper is where you'll find the authors framing the context of their research. They'll be talking about background information relevant to the question they're asking and the work they're doing. And in this case, I think the first paragraph is pretty informative. They start by saying that several studies have documented the antibody responses, that is, after 2 mRNA vaccinations, and after a third immunization, where the antibody response was superior to just 2 doses with regard to their neutralizing capacity against a broad spectrum of SARS-CoV-2 variants. It's very important to recognize that these mRNA vaccinations with just 2 doses or 3 doses give you a very broadly neutralizing capability against a lot of SARS-CoV-2 variants. And again, this is talking about only the ancestral Wuhan strains in the monovalent vaccines. And again, with the third dose, you see superior neutralization capabilities compared to 2 doses. If you're not sure what neutralization capability is, we'll get there in a little bit. They also say in this infection that prior research showed that antibody avidity increased after mRNA booster vaccination, which was partly explained by prolonged germinal center activation and ongoing B cell maturation. This is also really interesting because antibody avidity is another function that we care about with antibodies. You might hear a lot about affinity, which is how strongly an antibody binds its target, but avidity measures other functional components of that antibody, including how many molecules it can bind. So that also increased after mRNA vaccination, which is pretty cool. It's something that we probably want against a quickly evolving virus like SARS-CoV-2. And they explain this phenomenon with germinal center activation. That's something that we'll talk a little bit more about later. But all very important stuff to frame the context of this conversation. And the last few paragraphs of their introduction talk about what they are going to do. So they say that in prior research, there was some research into the kinds of antibodies that are predominant during an antibody response to vaccination. They say that IGG1 and IgG3 are found to be predominant classes, whereas IgG2 was rare, and IgG4 was almost undetectable. But responses to long-term development of this immune response, including a third dose, had not been analyzed yet. So that's where these researchers come in. They are looking to characterize the antibody response to mRNA vaccination. So with that, we can go quickly into the results. And by the way, if there are any questions during this time, I'm not going to be looking at the chat. But if you raise your hand, then Indy or Professor Zeno can call on you and we can have a question.
Yeah, please do request to be a speaker because we definitely want some people to come up and talk.
Absolutely. So the researchers in their experiments gathered a cohort of healthcare workers, and these healthcare workers had their vaccinations of mRNA vaccination, mostly community, the Pfizer mRNA vaccine. And during this study, none of them were found to have had a SARS-CoV-2 infection until the time period of between their second and third doses. And I think about 10 of them, this paper says, had an infection during that time period. And so that data is all included in this data set. So what you're looking at is mostly the response of vaccination and not infection. So what they did was let me just get up the first figure here. They started looking at the population of antibodies in the sera of these cohorts. So if you look at figure 1b specifically, they're measuring different kinds of classes of antibodies, IgGs1 through 4. And in case you didn't know, which would be important background for this paper, but this paper doesn't specifically talk about the background of antibody classes. Antibodies can have classes. There's IgG, there's IgA, IgM, IgD, and IgE. And those different letters of classes can be further divided into subclasses. And in this case, we're just talking about the IgGs and the 1 through 4. They have slightly different functions, which I'm going to talk a little bit more about later. And if you want to learn more about the specific kinds of antibodies and what they do, then you can certainly learn more about that on your own time. But in this case, we're looking at populations of antibody subclasses, IgG subclasses, depending on when the patient was vaccinated and with what dose. So in figure 1b, starting with IgG1, before any vaccines, the level of S, or spike protein specific antibody, is pretty much non-existent. It's at their lower limit of quantitation. That means that's where the assay can not detect. Anything below that means that the assay didn't pick it up. But after the first dose of mRNA vaccination, you see those numbers start to go up. And after the second dose of mRNA vaccine, that IgG1 is well above the limit of quantitation for everyone involved. That means everybody had an antibody response. Everybody produced antibodies against spike. That's great. That's what we want mRNA vaccines to do in this case. And then you see at the x-axis at the bottom, they have a FU post-second. That's a follow-up post-second. That is a number of months after the second dose. What do the antibody levels look like? And you see the antibody levels start to go down. This is exactly what we would expect an immune system to do. An immune system is not going to constantly expend energy to keep antibody levels really high because it has something called immune memory. So that's nice to see in this assay. But then after the third dose, those levels shoot back up to practically the same levels as before. And in a follow-up post-third, you see that those levels are still there. And the ones with gray dots, those are the ones who got infected between the second and the third dose, their antibody levels are generally higher. So that's not surprising. And this trend generally remains consistent when you look at the IgG2 subclass. It's a little bit different with the IgG3 subclass. Those IgGs tend to go away with more doses. That's a function of immune maturation. We don't need to go into that. But the interesting observation that they notice in this first figure is when we get to IgG4. So before the follow-up of the second dose, IgG4 levels are practically non-existent in the sera of this cohort. But after the third vaccination and following into the follow-up of the third vaccination, we see IgG4 levels are increased in most of the participants in this study. Also cool to note that in the IgG4 panel there, you see those 10 gray dots, the people that got infected, their IgG4 levels are the highest follow-up post-third infection, post-third dose, excuse me. So this was a really interesting observation that this paper was kind of, when it was written, kind of centered around. this IgG4 increase. And so panel C there just shows you the proportion, percentage-wise in a pie chart, of these different IgG subclasses, either in the post-second dose, follow-up, post-second, or follow-up of the third dose. So, interesting. IgG4 antibodies are increasing. So what more can we learn about studying these antibody responses? Well, the authors kind of alluded to this in the introduction when they talked about germinal center maturation and kind of this maturation of the immune system. So the next thing they do is they want to monitor the immune cells in a longitudinal sense moving forward. So if you just move down to figure 2A, that you can see kind of how they started to do this. So in figure 2A, we have a nice flow cytometry figure. For those of you who don't know what flow cytometry is, just Google the words flow cytometry, start reading, and then be amazed because it is a really fantastic technology. Essentially, what you need to know about it in this context is that it's a way of sorting specific cells based on particular markers that they might be expressing. So in this case, they have B cells. So they're isolating all of the B cells. And the way you read this flow cytometry chart is in that first picture in panel A, there's a y-axis called CD27 and a x-axis of CD19. All of the cells that are expressing CD19 are going to be boxed down in the lower right, and all of the cells expressing CD27 would be boxed up in the upper left of the graph. In the bottom right, or in the top right of the graph, you have cells expressing both CD19 and CD27. And so the instrument is able to sort the cells based on what they're expressing. They further divided the cells into cells that were only CD27 positive and measured the ability of the cells to produce antibodies that can neutralize spike. And they pretty strikingly found that almost all of the B cells that are producing anti-spike antibody in this case are CD27 positive. And that's interesting. They don't really explain it in the paper, but it's interesting because CD27 is a marker of B cells that are carrying somatic hypermutation. So these are B cells that are actively shuffling their IgG genes, and that's a sign of immune maturation. And that's really cool to see with this immune response, that there are so many CD27 cells producing spike that are undergoing somatic hypermutation. And you can see that these cells are present in follow-up post-second, post-third, and follow-up post-third individuals. The amount of these cells significantly goes up between the follow-up post-second and the post-third, but between the follow-up post-second and follow-up post-third, they are not statistically significantly different. So, are there any questions about this so far? If not, we can keep going.
And I think a lot of people are working, or a couple are busy DMing me that they're busy, so we might not have too many speakers. But again, if anyone's free, just feel free to come up.
Awesome.
Hey, I have a quick comment question. Looking at the layout, I know it's in there. It's a little, I'm always looking for that section that starts with a capital M for method, and they've got results, but their method's a little narrative spread out. It's a little bit hard for me to track. I just want to lodge that not so much a complaint, observation. Sometimes, printing the paper out, you get it. It's easier to see. This could be a digital artifact for me as well. I don't. You don't have to address that. It's just a thing for me.
Oh, no, totally. So the methods in this paper are going to be towards the bottom of the page. Their method sections are
Got it.
towards the end of the paper.
So I see it now. Thanks. Yeah.
Yeah, and usually in a science paper, the methods will be extended in a supplementary file. In this case, it looks like a lot of the methods are written out pretty extensively on the main page of this paper, but it's not uncommon to have most of the methods in the supplementary part of a science magazine article.
Yeah, and that is a feature of science often, that it's in a different location so they can get right to the results. Thanks.
Mm-hmm. Yep. All right. So they were, after seeing these observations, they were curious about the IgG4 producing B cell clones. So again, this observation that IgG4 doesn't seem to increase until follow-up post-second or especially post-third dose was interesting to them. So the next thing they go ahead and do is they do there's some work in the supplementary materials where they look more at these IgG4 specific B cell clones, but then they also start to do more comparisons of the antibody response in terms of function, and that's what they're getting at in figure 3. So antibodies have functions. They do some different things depending on the type of antibody it is. The general anatomy of an antibody, maybe we can have a little picture of it in the nest. Someone can do that. But if you go to figure 3G, you can see a little cartoon of some antibodies. They're in a Y shape. The top of the Y is generally going to be the parts of the antibody that bind a specific target antigen. So an antibody will, depending on the top of the Y part that it has, it might bind spike, it might bind an N antigen, it might bind something completely different. The point is the top of the Y is what makes it specific towards a particular antigen. The bottom of the Y, called the FC portion, the fragment, I think it stands for fragment crystallizable, that is going to perform other functions. So once an antibody binds its target, it can either neutralize the target or it can just kind of stick onto it. If it neutralizes the target, that means that the target antigen that it has bound can no longer perform its function. So, for example, in the context of spike, if an antibody binds the spike protein, and then the spike protein can no longer bind to ACE2 because it's got a big honking antibody attached to it, then that's a neutralizing antibody. However, if it binds it at a spot that doesn't interfere with the ACE2 binding, that's a non-neutralizing antibody. But non-neutralizing antibodies can still perform functions with their FC portion. And figure 3 is going to talk a little bit about that. You'll see the abbreviations ADCP and ADCD. These acronyms stand for antibody-dependent complement deposition or antibody-dependent cell phagocytosis. So taking those in order, complement deposition means that if the antibody binds its target and it wants to call in backup to the site where it's bound its target, then it's going to deposit complement through a series of interactions mediated by that FC portion. Complement is just, you think of it as an alarm system of the immune system. It's going to call in more white blood cells, it's going to call in inflammatory factors, and it's going to just ramp up the immune response in that particular area where the antibody has bound the target. Antibody-dependent cell phagocytosis is when an antibody is bound its target, and through its Fc portion, another cell is going to recognize, hey, this cell has been bound by an antibody, or this foreign object has been bound by an antibody. I should eat it. And so that's what that antibody is helping to do. But sometimes antibodies might not have an Fc function. Sometimes they just neutralize. In this case, IgG4 does that. It does not it does neutralize, as we'll see in this figure 3, but it doesn't have Fc function. And we'll talk a little bit more about why that might be important in the case of a COVID infection in a little bit. But just looking at figure 3, again, this is taking serum from their cohort, and it's quantifying the amounts of antibody subclasses in panels A and B again. I believe panel B is looking, specifically at IgG4. Again, reiterating that this IgG4 doesn't really show up until post-third dose dosing of mRNA vaccine. And that's just a theme that you'll see often in scientific papers. They often will show figures that repeat similar things that you've been told before in the paper, just to drive home the point that they're measuring a real result. And if we go down to the later panels, C through I, panel C is measuring avidity. That is the other functionality that I mentioned about that antibodies have. So avidity is going to be measuring the overall strength of antibody interaction and how it's influenced by 3 factors. The affinity, so avidity is influenced by affinity. The valency, which is how many molecules the antibody can bind. For example, can each Y arm on the antibody bind its own target? Or can an antibody dimerize, like an antibody like IgA can bind with itself at the Fc portion, and then that molecule can then bind 4 target antigens theoretically. And also the structural arrangement of the antibody is also being influenced in avidity. All of these things can influence how an antibody functions. And generally, you want avidity and affinity to be really high, really good, because you want antibodies to bind tightly to their target, and you want them to be able to perform these different functions. So after the 3rd dose of mRNA vaccine, you see avidity overall goes up. That's good. You also see that neutralization against spike goes up. You also see that neutralization against Omicron goes up after a 3rd dose. Remember, this is monovalent ancestral strain mRNA vaccines, but you still get significant increases in Omicron neutralization. That's pretty cool. And all of this is despite the fact that we have all of this is within the context of IgG4 increasing in that 3rd dose. So we see all of these really good things happening with the antibody response post 3rd dose, with that IgG4 being increased in the population of antibodies. So the rest of the figure, G through I, is talking about those effector functions, the Fc functions of these antibodies. The antibody-dependent complement deposition, antibody-dependent cell phagocytosis. Interestingly, those things decreased after a third dose. Those capabilities of the overall antibody population taken from these patients decreased. So that meant that when they take these antibodies from these patients and test how well they can tempt cells to eat their target or deposit complement on their target, that decreased significantly. So that, I think, is where a lot of the misinformation about this paper came from. But I'm just going to finish up this discussion portion before going to that. So overall, the authors found that IgG4 subclass antibodies increase after the third dose of mRNA vaccine. This was in contrast to other vaccines, vector-based vaccines, where we did not see this increase. And this is the reason is speculated to be that mRNA vaccines just are really good at inducing germinal center formation. Those are the germinal centers are structures within lymph nodes, which are immune organs, where B cells essentially go to school to learn how to do things better. They sit in a germinal center and they learn how to make better and better antibodies. And the longer a germinal center persists, the better it's going to get at doing that. And we know that mRNA vaccines from other work are really good at stimulating germinal centers. So it seems like the better germinal center responses are going to be more associated with this increase in IgG4. And the authors also reiterate that this IgG4 might be coming up because, in their words, it is conceivable that non-inflammatory Fc-mediated effector functions reduce immunopathology, whereas virus is still being neutralized via high avidity antibody variable regions. So if I can translate that for you, they're saying that the non-inflammatory functions of IgG4 are favorable in the case of a COVID infection, possibly, is what they're saying. So remember, IgG4, the Fc portion, doesn't have those capabilities where it can deposit complement or encourage cells to eat its target. It's just going to neutralize. And so why might that be advantageous? Well, it means it can neutralize a SARS-CoV-2 particle. It can prevent it from spreading in its infection, from infecting other cells by neutralizing the spike protein and preventing that binding to ACE2, while also not ramping up the immune response. That's what they mean by reducing immunopathology. Because if you've been following these spaces for some time, you might know that in a COVID infection, the dangerous part is actually from your immune system, what we call a cytokine storm. Basically, it happens when the virus spreads across your body really fast before your immune system can get a chance to control it. And then you have virus all over your body, and your body is going into an overdrive emergency mode where a lot of inflammatory molecules are being produced all at once. And those inflammatory molecules are causing damage to your organs, causing you to go into respiratory arrest, all kinds of things. So maybe the body wants to mitigate that in this case by increasing the amount of IgG4 to the point where it's not the dominant antibody in your antibody pool, but it's there enough to maybe dampen the immune response so that you get just enough that you're able to quickly neutralize the virus, clear out infected cells, and avoid immunopathology, avoid that immune damage. So that is wrapped up in that little sentence there. But this is a science article. Words are very tight. Character counts are very tight in each article, so they can't say all of that. And I think to end off, I'll just read their final paragraph, their summary section. They say, in summary, our study demonstrates mRNA vaccine-induced antiviral IgG4 antibody response appearing late after secondary immunization. Further investigations are needed to clarify the precise immunological mechanisms driving this response and to evaluate whether an IgG4-driven antibody response affects subsequent viral infections and booster vaccinations. This is relevant not only for potential future vaccine campaigns against SARS-CoV-2, but also for new mRNA-based vaccine developments against other pathogens. I think this last paragraph, because usually it's either the introduction or the last paragraph in the paper that gets misrepresented the most. I think this paragraph is what a lot of the misinformation is being it is being used to fuel. So what they're saying here is that we don't know everything about this IgG4 antibody response. They didn't test it. They didn't test every aspect of it. Their paper has no relevance to clinical outcomes. They just observed the phenomenon and did some characterization on the cellular and neutralization capabilities of these antibodies. So they say, this is our work, and this is what others can do to learn more. But if there's ever a sentence in a paper that says we don't know or we need to learn more, that can be abused by people who are disingenuous. What we know from this paper is that the neutralization capabilities of an antibody pool for someone who has had 3 mRNA vaccinations is very high. So the antibodies are able to neutralize very, very efficiently, but the pool of antibodies are less good at doing things like cellular mediated antibody functions. Is that bad? This paper doesn't say anything about that. This paper just measures the capabilities of the antibodies. If we want to know whether or not that's bad, we can look at clinical outcomes. We can look at who does better. Is it people with 0 vaccinations, people with 2 vaccinations, or people with 3? Well, I think that we can find many links to put up in the nest that people with 2 vaccinations do better against COVID than people with 0 vaccinations, and people with 3+ vaccinations do even better than people with 2 vaccinations. So this is really an interesting exercise in immunology and what the body prioritizes when it's going through immune maturation responses. I think it's really, really cool that in this case, the body is actually picking non-neutral or non-FC effector functioning antibodies as something to prioritize a little more than we might expect, because COVID causes such an inflammatory response in severe cases. And that is borne out in, I think that the fact that that's a good choice for our immune systems to make is, I think, borne out in this study showing that the neutralizing capabilities are really good, and the clinical data showing that the outcomes from severe disease are also really good. So I think that that's all I wanted to say about this. I guess I'll just mention as an end note really quickly the way they did these neutralization assays, since it's such a big part of the paper. I should maybe explain how that's done. It's just a pseudovirus neutralization assay, where essentially what they do is they have a pseudovirus, and they have the antibodies taken from the patients. The pseudovirus is just kind of a vector virus that is expressing spike protein. So they have cells that express, or they have ACE2 in a system, and they have the pseudovirus and the antibodies, and the pseudovirus and the antibodies compete for binding of ACE2. And the output of their experiment is measuring which one does better. So that's how they measure neutralizing antibodies. Yeah, so that's the paper. There's a lot more to it. If you want to learn more about it, then definitely read it cover to cover for yourself. Google words you don't understand. Take it slow. Reading a scientific paper is often really tough. And check out the links in the nest. There's also going to be a little, if you go to the page where this paper is, there's a little, there was an article written about it in Science called "Is it good? Is it bad? Is it good? Or is IGG4 just misunderstood?" And it's a focus article, so it just basically explains what this research paper means in a scientific context, and says a lot of the stuff that I just said. And with that, I think we can definitely open it up to questions.
That's great. We don't have any other speakers up in the panel yet, so please submit your requests. I'll kick off with just a little framework, and that is, well, first, I appreciate the talking me through it, because I would not have been able to get that much out of the paper without that. Second is, like, in the world of empirical research, it comes in different flavors, and this is really interesting type of research because it crosses some domains. But fundamentally, what this seems to be is basic research as opposed to applied, practical, or even truly clinical research. It has clinical data, but it's really, I mean, maybe this is a good debatable point, but is it more than basic research, meaning it is answering questions about immune response with some clinical data, but it's applied. There's some I don't know, maybe this is applied immunological research, but there's something very basic about it, which doesn't mean it's bad. Basic research gets us the building blocks of here's what the immune system is and does and how it responds to vaccination doses. But it doesn't have that final answer that maybe some people are looking for when they're looking for that ideal. That, there is no true Scotsman, no perfect test. One study will not do it, will answer every question we have. So what do you think about that? Is it still basic research about immunology?
Yeah, I'd say this paper is basic research on immunology because they're studying fundamental questions of what happens to the antibody response over time and after more exposures. There's definitely a big clinical component to it, but this paper, I mean, it's really important to understand for anyone in the audience who might not read scientific papers regularly, what the scope of each paper is. One paper is usually not going to test like a ton of big questions all at once. Each paper is usually kind of just drilling down into one question, which might be really a really small but important question. It might be a really big question that affects a lot of things, but it's not going to talk about all of those things. It's just, you have to look at the paper in its context, and then if you want to kind of broaden it and apply it to other things, you have to ask, okay, what other data sets ask this other question that this paper doesn't talk about? And can I maybe get an answer by looking at that data set too while I think about this one?
Right. And then it's often time to move on to another study. Like, okay, what published, trustworthy empirical evidence is out there that answers the next question we have after reading this source, right?
Right,
okay.
Right.
Yeah, we got a couple speakers. So I think Wes came up first, and then we'll add Dr. Wilson and Dr. John Michael. So Wes, what are you thinking? How's your summer going so far?
Busy, lots of work, still at work, doing the work thing or listening along. So, one thing I just wanted to add is that these similar findings were found in another paper as well. They were published in May. I think the paper we were talking about was published in January. I put it up in the nest if you want to check it out. They looked at a couple different things, but one of the things they found was very similar to what was found in this paper.
Yeah, and thanks for that, Wes. That's always good to look in the scientific literature to see if others are also finding similar things, because, I mean, especially with COVID, I don't think there's any one lab that is the only lab investigating a particular question. I mean, there are so many labs around the world all investigating all these different questions, and it's worthwhile to look at what each of them find independently of each other.
for sure. Converging evidence. And yeah, science is quite, impressive to, have your study published in. And there's not a lot of space. So they didn't have a lot of time to relate to other research, but definitely it's an emerging field. I think I can read, what's cool about this discussion is I think I can read other sources with a little more understanding of what I'm looking at. Dr. John Michael, you on staff today?
Oh, I'm just finishing up since I'm leaving this hospital soon. But yeah, I'm moving shit back and forth to storage. But yeah, it was a really excellent paper discussion. It's kind of a basic science, kind of like a grassroots, kind of ground level thing. And we, this kind of study we kind of build further studies, as you guys all alluded to. I think the basic science and immunology behind it's key to understand, and I think overarching that there's so many different effects of different immunoglobulins, and the specific type is definitely one that seems more immunologically mediated, like in terms of autoimmune disease. So it'll be interesting. I know Kevin Bass wouldn't get this, but IgG4 is like the word question. That it's linked to autoimmune pancreatitis. They'll be like, what IgG is linked to autoimmune? And it'll be like IgG4. So, he wouldn't get that one, obviously. But, looking on this, I think, it's one of those things, it's the chicken or egg kind of thing. Is it something specific to COVID, or is some IgG4 mediated, that is more common? So I think, I think the whole cytokine storm stuff, like you said, Dr. Dan, I think, did you come across anything ever with like super antigen effects, not just like cell mediated with IgG4 as well? Right there. I got time to.
So, oh yeah. So, nothing comes to mind about super antigen mediated effects in this context, but maybe someone else knows. But you did mention a good point. Like, does other immune insults cause a similar immune maturation response? So, like, does influenza cause this kind of immune response over time? I'm not sure if. Oh no! I was gonna say, I'm not sure if people have really looked for that. I'm not sure if anyone's really, given multiple doses of, say, MMR vaccine and looked at the specific subclasses of antibodies at different time points after different doses.
That'd be really yeah, go ahead.
Yeah, I was going to say immunology. We've learned a lot about immunology over the course of the COVID pandemic, partly because a lot of resources have been dedicated to studying these kinds of questions. So immunology has gotten a little bit of a boost in the scientific community as far as what kind of work is being done. But yeah, I'm not sure if anyone's looked. I'd be really interested to see if anyone knows anything data.
Oh, before Wes, I'll put it to like a sensitivity versus specificity, with IgG4 and COVID too. It's like this something that IgG4 is going to be present in, found at all, but like we talked about, like, is this other, like you said, other vaccines could it cause this? So is this a sensitivity or specificity or both, right? So I'll yield to Wes.
Yeah, I mean, I was actually going to say the answer kind of to your question is that we've seen this kind of class switching, IgG3, IgG4 with other vaccines, protein-based vaccines. It's not in all protein vaccines, but it is in some. And we don't really know why some create this IgG4 response and others don't. Like, we don't know why that happens, but we have seen that in other vaccines. And around sort of, modern kind of vaccines, the HIV vaccine, the VAX-003 trial, they used two different recombinant proteins. And in one of those proteins, they also reported IgG4 class switching and antibody predominantly produced. So, I mean, it's not a new finding in terms of vaccine IgG4 antibody response. So that's like that discovery is not novel to the COVID mRNA vaccines by any length or stretch of the imagination.
Yeah, I remember that now. There was what you said about the HIV vaccine candidate. And I believe in that context, it was actually not desirable because, well, HIV is just an entirely different beast than something like SARS-CoV-2. In that context, you would really want more antibodies that are good at specifically killing infected cells, because HIV hides out in cells, immune cells specifically. It's just really, really difficult to make a vaccine towards HIV. And neutralizing antibodies are really good against preventing an HIV infection, but once it's in, neutralizing antibodies aren't going to get rid of it. But I do remember that some people use that bit of information to claim that IGG4 in this context is bad, but that's just not right because, again, HIV is a completely different animal, completely different functions, and you want completely different outcomes from an immune response against it.
Yeah, I think you're right. I feel like it's a bad thing. I mean, IgG4 can like form complexes with IgG1 anyway, right? So
Yeah.
And I think in this study, one of the slides up there on the deck that Independent put up there, I think IgG1 numbers were, well, not statistically significant. They're higher at those same high time points as IgG4. So you could theoretically assume you're getting both, right? You're getting both types of inhibition and clearance from the IgG4. So I don't think there's any argument to be made that IgG4 numbers or class switching in general would be means that it's not working or that it's bad. I think there's two sources of evidence to suggest maybe it's good. So yeah.
Yeah, and that'll be
what you're saying, Wes, right? Sorry, but yeah, good.
I was gonna say, and then we can get back to you, John, Dr. Dunn. Yeah, that would be an interesting question to see. Is IgG4 complexing with IgG1 in this case, and does that have any significant function in the context of COVID and SARS-CoV-2 infection? And those are the kinds of questions that I think the authors are looking to for the rest of the community to ask. Like, how is this working? What is successful or not successful about this antibody response? And what can we learn from it to better inform us when we're looking at immune responses to other vaccines? I think that's a really good way to frame like what the authors are hoping this paper inspires in other scientists.
I mean, Wes, have you noticed anything similar with like protein-based vaccines or treatments for like, oncogenes like cancer and whatnot as well, or that's thinking it's popped up as well?
In terms of protein-based vaccines, yeah, like this has been reported in the past 20 years. Again, IgG4 is probably one of the most poorly understood classes of IgG in terms of its evolutionary function and how it came about. But people have reported this across many protein vaccines over the years, but it's not in all of them, right? So like some protein vaccines, we don't see this at all, and we do see it in some others, and nobody really knows what's causing it, what makes that class switching occur.
I mean, it's almost like, with especially like with cancer and, surveillance of the immune system, is this something that could be, used for, kind of, increased surveillance for catching like the, malignant cells or the ones that aren't, functioning correctly, so it's pretty interesting.
As a pure thought experiment, John, I think that's really cool and really interesting. Here's my thing. Here, I'm just gonna play devil's advocate because I think what you're saying, John, is very, very interesting and is worth some study, and I think someone should look into it. The devil's advocate from the existing data that we have from this class switching from antigen, immune response, is that the inconsistency between external antigens, which would then apply to neoantigens found in tumors, would be that it'd be just as inconsistent in class switching. That it would probably work. 50% is not the right number. I think it's less than that. But let's say it was like 30% class switching on antigen exposure, continuous antigen exposure stimulation. Then neoantigen would only work 30% of the time for detection of cancer. Playing devil's advocate, I do think what you're saying, John, is actually a really cool concept and something we should look into. In real life, I think that's a really cool case.
I mean, especially like in the ones that already do like interleukins, like, you know, like melanoma and, you know, renal cell cancer and whatnot. I mean, there's some potential, I would think, but like I said, that's your bag. I'm just being a nerd here. So yeah, that's it.
I love being a nerd, John. Love it. Love it a lot.
Oh, and I wanted to comment, Drew, your profile pic looks awesome. It looks badass. As a listener.
Yeah, I like it. I think let's see, I'm gonna have a bit of a hard out in about 20 minutes or so. So I wanted to quickly specifically address a lot of the misinformation that I've seen around this paper. Most of you are aware that Makis was among one of the authors who wrote basically an opinion piece. I think it was in the NDPI predatory journals. But it's fueled a lot of discussion about this paper. The main claims that I've seen that are wrong. People say that for immune dampening, that it's similar to an allergy response. And the implication of all this is that it means that our immune system is becoming tolerant of SARS-CoV-2. And instead of eliminating the virus, we're just going to keep it around in our bodies longer. And that's going to make COVID infections worse, is the implication. And the obvious big problem with that is that there's absolutely zero evidence for any of that. Not only do people who have had their 3 doses of mRNA vaccine had better outcomes than people who have 0 or even 2 doses, we also know that people who are vaccinated clear the virus out of their body faster than people who are not vaccinated. And it's because they have an immune memory response that kicks in with cellular and antibody-mediated immunities that will both neutralize virus and clear infected cells. It's just completely wild to me that people are making those claims based on this misunderstood result while completely ignoring the clinical data that completely refutes it. Again, the whole idea of their whole idea of immune dampening is wrong, because yes, it's the immune system adapting to reduce immunopathology, but it's not eliminating those antibodies that have that Fc functions, and it's still able to neutralize the virus, which if you neutralize virus, then you pretty much stop it dead in its tracks, and it's not going to be able to do anything. So yeah, I don't know what else is making people believe these things, but those are the main claims that I've heard kind of summarized in quick succession, and why they're wrong. But if anyone else has anything to add or any ideas as to why this idea is popular, then I'm all ears.
Nope, I had to sit that one out because I had no idea what IGG4 was. But I generally know the anti-playbook, take something that's a seed maybe of truth from a study and twist it to conform to your thinking, instead of looking, at it more realistically. And then, okay, what's another study that would debate it, that would challenge it?
Right. Yeah, they really twisted this one. I mean, the kernel of truth that IgG4 reduces immunopathology, which is a good thing, has been twisted into this idea that you're not having an immune response at all and you're letting the virus persist. It's wild. Maybe even clever on their part to take a complicated topic like immunology and make a wild claim that anti-vaxxers are going to believe. But maybe that's giving them too much credit.
Well, I do think there are some people in their machinery that are smart enough to know how to do that. or have been trained up in that through other ways, practicing a rhetoric that simplifies and pits one against the other, that feeds into a culture war rather than an honest scientific conversation. That's what journal club's about. I mean, bring it. And you can go too far if you don't know what you're talking about and say something stupid. I think I avoided myself of that because I do not know immunology. But if anybody else wants to pop up here for a question or a comment, like I said, I did it without, I think, making a fool of myself. So these guys are very knowledgeable who have spoken so far, but feel free to jump in if you've got a question or comment. While we have a few more minutes with debunk. Are we keeping track? Is this the third in the series, Indy?
Yes, third in the series.
Yes. And it's cool because each one's taken a slightly different tack.
Actually, fourth in the series.
Oh, fourth. That's right. Fourth. I missed one.
And we do have one, I have to confirm with P&W, but we do have one scheduled for next Wednesday, actually, that I'll be sending out shortly about chorea myocarditis.
Excellent.
That'll be great.
Yeah. And I do think it's right to keep it, we don't have to do these marathon sessions and take on every topic. That's what, this is kind of an exercise on. It's like, hey, can we stay focused? We don't have to bring in all the other issues or concerns related scientifically nor socially. We make this, then the space stands up over time. It's still useful rather than talking about what everyone's going through this week. Yeah. Dr. Pacific Northwest has entered the chat, as has our junior anatomist. So if you guys want to pipe up, please do.
I was just going to quickly say, as someone who has an extremely surface level understanding of IgG classes and how they all work, thank you very, very much to Bunk the Funk for your explanation of that paper, because you made it sound so clear and concise, and it all just made sense to me, and I'm really, really glad that I came along and listened. So thank you very, very much.
You are very welcome, Kat, and thank you for making Steve Kirsch look like a fool.
Anytime. I would do it again, but he's blocked me.
Same. He blocked me too.
Hey, Dr. Dan.
Hey.
I'm trying new AirPods. I hope they work okay. Same thing. Well done. Taking such a really difficult paper and breaking it down. I haven't thought about this stuff in 20 years, and nice and crystal clear and to the point without a lot of extraneous. Very well done.
Thanks, I appreciate that. Yeah, there's a lot in here. There's definitely more about the specific IgG classes that I didn't want to go into, but yeah, I'm glad it was clear.
It really was. And I think the two things that makes me want to learn more about now, which is a really important function of having these kind of journal clubs, is, what's the clinical implications of these findings? For example, in somebody that had a high response versus a low response, and how they did over time. And also, what's the difference between infection and vaccination responses?
Yeah, I mean, those are really interesting questions, right? Like over the course of the pandemic, I think there's been a lot of talk about, which vaccine produces higher titers of antibody and whatnot. And I think that, it was shown that maybe Moderna is able to produce a little bit higher titer than Pfizer, but then it's like, does that matter? Does it really matter? Like, if in this context, we took someone who got a third dose and for whatever reason didn't produce IgG4 in the quantities that we see, like we were able to have a model system where we can shut off IgG4 production and then measure disease outcome. Like, would it matter? I don't know. It's a really interesting question, but that's like, I think what these basic immunology studies are really trying to get at, because at the end of the day, we can look at this paper and ask all those interesting questions, but we can also just look at the clinical data and say, well, 3 vaccines are working. We don't know exactly how or why they work as well as they do, but we know they work. And we have a lot of smart immunologists who are working to understand the nitty-gritty details of why. Wes, I think you had your hand up.
Yeah, I mean, the study I linked above looked at a few more things than just this. But this paper is looking at antibodies specifically. Although I think they underused their single cell sequencing, in my opinion. But they did. There's other components. We know there's other components. This paper's not claiming there's other components. There's a huge T cell component to viral clearance for SARS-2. And this paper is just not about that. This paper is about something else. It's like reading Goldilocks and the Three Bears and being like, how come they didn't explain what happened to Neo at the end of Matrix 2? And it's like, well, that's a good point. It's important to know what happened to Neo, but that's not what this story is about.
Yes. I mean, a whole other arm of immunity, T cells, not even talked about in this paper. So, yeah, T cells, for those who might not know, are immune cells that function in a completely different mechanism than what antibodies and your B cells do. And the way that T cells recognize and react to their antigens is completely different. So if your antibodies don't work, but you have T cells, then you can still fight off disease. So, the system gets more and more complicated the more you learn about it. So it's not as simple as seeing a rise in a particular antibody and then correlating that to a clinical outcome. It could be a completely different component of the immune system that's actually responsible for that clinical outcome. And you definitely need to look at more than one paper to figure that out. But I think that's asking a lot of people like Makis and whoever else is spreading this nonsense about this paper. EW, had your hand up?
Yeah, I was wondering if you guys know, any of you, if there is a way to measure laboratory-wise commonly T cell function as opposed to IgG levels.
Yeah.
Yes.
There totally is. And the types of function, it gets a little more nuanced. There's like for example, just one type of T cell, a CD8 cytotoxic T cell, has 3 different states of exhaustion signatures. There's like stem cell exhaustion, effector memory exhaustion, and terminal effector exhaustion. That's just exhaustion. That has nothing to do with central memory, effector memory substates. There's so much with T cells that you can test in a laboratory setting. But ultimately, the short answer is yes. We can definitely look at T cell function and dysfunction and dysregulation.
Yeah, and there definitely are assays to, in a laboratory, look at like your T cell immunity. One common one is called an AIM assay. It stands for activation induced marker. So T cells are going to respond to T cell epitopes. So what the assay basically does is it takes T cells and then throws peptides on them. Peptides are just short pieces of protein, and measures their response. So you can measure how well and to which peptides T cells react against something like spike. But traditionally, T cells are harder to study in a lab. You need specific equipment. The assays are more involved, and that's one of the reasons why it's just not as common. It's relatively easier to take serum from someone's blood and do a quick neutralization assay to look at the antibodies. And it takes more time and more resources to look at T cells, but the assays do exist.
As a caveat, as a T cell biologist, as a caveat, I will say that, I mean, it's not that T cells are harder to look at per se as any other cell. It's more like, when you're looking at antibodies, you're basically just looking at a protein, as opposed to B cells that produce antibodies. Studying B cells is probably just as in depth as studying T cells per se.
For sure. Yeah, I wanted to make it clear that it's the time and resources involved in studying T cells that I think.
But this study did look at cells, right? Because if I remember correctly,
yes.
They did do single cell sequencing, right?
Yes, they sequenced the B cells. That's a part I didn't talk much about, but that went into the discussion about the fact that these B cells are undergoing a lot of somatic hypermutation. In academic labs, studying B cells and T cells, I'd say are pretty comparable. But in a clinical setting, when we're talking about immunity, people just test antibodies most of the time. Clinical settings don't often routinely test T cells because it takes more time. And you have to do a cellular component, whereas with antibodies, you can just take the protein. Is that right, Wes? Not accurate?
I mean, sure, close enough. I think for the purpose of this question, close enough. I think, again, different countries have different standards in their labs, for the pathology labs, and certainly different centers are different around the world, so I can't speak globally. But in terms of T cell panels and a basic flow cytometer, like, I'm not talking about like hypothesis generating new data from like, whole exome sequencing. I'm talking just like a T cell panel on a flow cytometer. That's relatively common in North America and pathology labs, in the hospitals. But that being said, I mean, in terms of, comparing this to just taking protein in the blood or looking at protein in the urine, yeah, it's more steps for sure, 100%.
So why do you think in the news cycle, I guess, or in the general science discussion online, T cells are pretty neglected, and everything talk about antibodies?
Yeah, I think for some people, especially a lot of people on Twitter who've all become freaking virology experts overnight, their understanding of immunology kind of stops at neutralizing antibodies, and they don't really know how they forget that T cells are a big component of this. I think T cell biology is huge. I think, since the 1970s, when we really got a good handle on T cells, our knowledge base is skyrocketed. It's a huge area within the T cell, within other fields outside of the Twitter experts. I think T cells are not ignored. I think they're a huge component in cancer research. They're huge because they're responsible for tumor clearance. They're a huge response in viral. Obviously, for HIV studies since the 80s, T cells are the ones that are CD4 T cells are infected directly by HIV virus. So, I mean, that's like a huge component of that research. I think within the communities, I don't really feel like T cells are ignored. I think media, journalists, and other people don't understand them well, so just sort of gloss over that component or forget about them. But I don't think people like, Debunk the Funk and PNW Doc forget about T cells. You can't. It's like Dre. You can't forget about Dre, and you're not going to forget about T cells.
Right. Exactly. Yeah. Don't forget about T cells, folks. Yeah. So anybody saying that IgG4 is bad and that we're going to have worse infections because of this observation is not only wrong about the data and what it says, but they're also not thinking about T cells. Zeno.
So when I hear that phrase, like these vaccines or the Myrna is like wreaking havoc on our immune system, is this kind of one of the sources that they have to back up that concept, or that they use because they misinterpret that way? Am I connecting the dots now?
Yeah, it's since this paper was published, it's that idea. It's definitely been used to push that idea a lot. That that our immune systems are getting weaker, and that's why we're getting more infections. It's not because Omicron is more antibody evasive. No, can't be that. It's the fact that these mRNA vaccines are doing it. Yeah, they can make sense.
Right. And then they'll appeal to this authority. Hey, even in science, they're publishing, got it. Yeah. And meanwhile, I just couldn't understand the study. I'm like, I'm not going in that one. I got my own business to worry about. So thanks for taking it on. I did add to the Nest dialogue back from, I think, just about a month ago. You were tagged in it. Seemed to include that a link to that paper, what Macus is trying to assert, and your debunking of his main points. So if anyone's curious on that history.
Thanks for that. I think we're getting close to the end here. Anyone?
Yeah,
Let's
it's been
put this
great.
all the
Wonderful one.
Yeah, Indy, I'll let you close out. You're the host.
No, Debunk, this was wonderful. Thank you so much for volunteering to present this, because I think a lot of us, even the doctors in the room, didn't understand it as much as, until you explained it. So I know as a layman, I learned a lot, and I had a lot of people DMing me about this particular space. So thank you so much. I did nest the space for next week. It's next Wednesday. I'll also be sending it out. So feel free to set your reminders for that one. But other than that, unless Debunk has anything else, we'll wrap it up.
I've got nothing else. Just pay attention to Indie Speed for the next Journal Club space. And yeah, everyone take care and check out the links in the Nest if you want to learn more.
All right. I'll leave it open for a couple minutes just so people can check the Nest, but we'll wrap it up and take care, guys.
All right. I'll hop up. See you guys. Thanks.
See you guys.